Okay, hello everyone, welcome back to the channel. My name is Mutanda Samir. Please, we are back again and still continuing with our we are still continuing with our we are still continuing with our Aitel revision series. Alright, and now on this we are trying to at least get there. Okay, good. Now we are in for our item 6 of our item revision mock examination. Specifically, we are handling physics. Right, good. Now please, we simply advise you, or anyway remind you, that we have, just like we are dealing with item 6 of Aitel paper, now in physics we are dealing with the standard paper. And of course, remember, physics has 7 items in a paper. Now here we strictly deal with theory, and this is paper 1. Now we are in for item 6, and sooner or later shall be getting you covered with the item 7. Now we kindly call you to go in the playlist. Please, you check and see we have right there from item 1, item 2, item 3, item 4, up right where we are. Okay, and just not only that, but we have a lot more of the videos. All right, then I will also send regards or a vote of thanks to whoever takes time to at least leave a comment on the video. Yeah, I really like that. Or then also I would also want to appreciate for whoever is watching this video and has already subscribed. Please, just know if you have not subscribed yet, you are doing a disservice to, I would say to me, but you are very many, so I would say you are doing a disservice to us and even to God himself anyway. Anyway, all right, let's proceed. That's just a simple joke. You can as well watch without subscribing, because I know a subscription is all about impression. Maybe you are not impressed yet, and of course sooner or later we believe you will be impressed and be on the same page with us. All right, without wasting time, let's get there. Okay, so we simply remind you to subscribe to the channel, like, share and comment. Share, like and comment in simple terms. All right, good. All right, good. There we are. All right, now let's get there. Okay, here we are. So they're saying let's make a follow-up. Okay, they're saying during an even downpour, by the downpour is more like rainfall if you're really keen about that, a sharp flash coupled with loud sound. Anyway, if it is a downpour, it's raining, a sharp flash and coupled with loud sound is a bit scary, were witnessed. Anyway, as a result, the whole village experienced a total blackout. Okay, total blackout here they're trying to mean, like, say for example, an area with the electricity and it's totally power goes off. That's what I mean by total blackout here. Okay, later it was discovered that a transformer had been damaged by a sharp flash. But of course, if it is, we got to know about a heavy downpour, a sharp flash with a loud sound, then again transformer damaged by a sharp flash, just think about lightning, of course, right there. The village organized the meeting to solicit funds to purchase a new transformer. It's a bit expensive, hoping they really got that amount they wanted. Okay, in attendance was the area member of parliament, MP, who promised the members that he was to purchase a device which can safeguard, why did he just buy the transformer anyway, safeguard the transformer against other damages from such a flash. I really see he would have bought a new transformer other than just getting a control measure. Anyway, even both of them, after all, he's an MP. Anyway, people wondered how the device can protect the transformer. After 2 weeks, the funds were raised and a committee was selected to go to town and buy a new transformer. The transformer dealer presented to the committee a transformer which supplies 12 volts when connected to a 240 volts main supply, and it takes current of 1.1 ampere from the mains when used to light 10 12V, 12 watts lamps in parallel. All right, good. So let's get there. Okay, good. So we proceed. All right, so I think this one wasn't that clear, but we shall still make a follow-up. So the same, the dealer convinced the buyers that the transformer had efficiency of 96%. Okay, now efficiency, like if I'm trying to explain this, whenever you're going to buy a battery, there's a machine where you can connect and see the percentage wise how better that machine can work. And of course, a 96% efficiency then means that it's really good, a good one by the way. Okay, so however, anyway, they were not sure of how the dealer arrived at that value. Using knowledge of physics, part A, find out whether the trader was trustworthy when he stated the above value. Part B, sensitize the community on how the device would guard the transformer against such destruction. So like here, a device which will safeguard the transformer from a destruction is simply a lightning conductor, if you can really think about that. Then find out whether the trader was trustworthy. That's about efficiency. Let's begin with part A. Wait, of course. Now, we are going to underline a few things here, if you try to be very keen. Now, we are looking at this efficiency of at least 96%, if you can really see that. So that means that our area of concentration must be about the efficiency. But again, before you go into that, we must first of all know how better can we get the efficiency. By the way, how can we get the efficiency? Now realize that efficiency in both categories, we have it that as okay, the formula for efficiency, you all know that efficiency is equal to, okay, we have what we call power output. Let me use letter P. We call it power output. Allow me use letter P to mean power. Then also here, power input. This is how we get free efficiency in and electricity times 100. That's how we get efficiency. Power output over power input times 100. But then a question comes, how shall we get the power output? Like say, the power output. Let's begin with that guy and we see how better can we calculate that. Then also, that aside, how shall we get the power input? Anyway, how shall we get that? The power input and power output. How are we going to get that? In fact, like in order to substitute into this, how are we going to get that? We need the power input and the power output to substitute here and here. The answer we get in terms of percentage, we shall compare it with the answer, the 96, which has been given to us in the question. I think with this, let's see. So then we shall now have to get the power input. The power input. Now, how shall we get the power input? Anyway, if you look at the transformer, like here, they're saying, let's add like they're saying, the transformer dealer presented the committee a transformer which supplies. Are you seeing this? So if this is our transformer, like this arrow shows the transformer is supplying. This arrow shows the transformer is coming in. Now here, in fact, let me use the different ink here. Please, here, this side is what we call input. Here is the input, what they are putting in the transformer. Then this side, the delivery coming out of the transformer is what we call the output. Hope this really makes some bit of sense here. So now, what input, output. Now this output is that which goes to homes. Now let's see. Okay, that's saying the transformer dealer. Okay, get ready here. Okay, transformer dealer presented to the committee a transformer which supplies 12V. Now, transformer supplies what? The total P this transformer supplies is 12V. Supply meaning that is giving out. So the V out here is how much? 12 volts. Is 12 volts. Okay, like that. Then, okay, what about this side? But of course, when it is supplying that, when it is connected to what? It is connected to a 240 V mains, meaning that is the input. So the PD, this side in the input column, is 240 volts. Okay, good. We proceed. And it takes current of 1.1. It takes current of 1.1. That implies that it takes, if the transformer is taking, it takes in. So this is the input current they are putting in the transformer. So the current I the transformer takes is 1.1 ampere, if you're really keen about that. Then from the mains, when used to light 10, how many? There are 10 lamps, if you can see, 10 lamps of what? Of 12 volts and 24 watts, meaning that now here from the mains, when used to light, if the transformer is lighting these ones here, then it is a power output. It's giving out a power output. So it gives us a power output, power also the power it gives out is of 24 watts. Now what does it mean? Remember, they have given us that the 12V supplies 24 watts, meaning that the 12V we had originally here gives us a power of 24 watts. But remember, we want a power output, meaning that we already have a power output. It is 24 watts, but this is only for one lamp. What about when there are 10 lamps? Of course, if there are 10 lamps, we shall need to multiply this by 10. So it means that the power output, we already have it. You multiply 24 times 10. Not about the power input. Do we have it? Not really. But we have the PD, which is 240, and we have the current, which is 1.1. But you all know that from formula, power is equal to IV. You really see that? Power is equal to now the 1.1 times the 240. That will give us a sanity answer in watts. Like that. Shall we be getting that? Now, what about here in the power output? Sorry, this is meant to be power input. Okay. Allow me just change this to power input. Anyway, that's power input. Then the power output is done showing us this arrow this side. Power output, power is equal to, of course, you get the 24 for one bulb times how many bulbs take that? 10 bulbs. So power output is just 240. That now you come and substitute in here, divide by that, multiply by 100, and you compare those values. Let's go there and see. Simply, let's get there. So we're getting part A answered. So we shall say that efficiency equals to power output over power input times 100. Alright, good. Now this percentage may not really be there. Okay. This percentage may not really be there. You can just multiply by 100. This may not necessarily be there. Okay, now next, shall now say that but power input equals to IV. But then reminding you that the current was 1.1 and the voltage was 24 volts. So we substitute in there. You realize that the I is done having right here, and the V is not having right there. When we apply, we get 264 volts. That is the power input. Remember, our aim is to get everything covered. We get a power output and power input. Then from there, we substitute. So we shall now say, but power output, so shall say now transformer lights 10 bulbs, each of 12V, comma. Now, are you seeing this word each? This word each means one, each of 12 volts and 24 watts, but we want this power here. Now, this 24 times, of course, the 10 bulbs. What shall we have there? What are we going to have there? So shall we say that total power output is equal to 24 times 10, which gives us 240. So we have the total power output, we have power output, and we have power input. Power output, we have it right there. Power input, we have it right there. Now, we shall again remind you of the formula. Efficiency is equal to power output over power input times 100. Okay. Now, what does it mean? We are going to substitute. Remember, our power output is this one, you put it there. Our power input is this one, you put it right there. So in a substitute, you get that. When you substitute, you get that. Okay. Now, we say 240, which are right there. And 264, we have it right there. Now, we substitute and have that multiplied. So when you apply, you get a 90.9%. Now remember, the shopkeeper told us that the efficiency of the transformers was 96%. But again, find that what we have is 90, so it is below. And if it is below, please, this man is not really good. And if I was not buying, that would be my first expression on this man here. Very annoyed actually. So he deceived them, I think. I think he really knew that maybe they couldn't make some of these calculations right here. So it was not, this man, he was not trustworthy in simple terms. Let's get that written. So he said that he was not trustworthy since the efficiency of a transformer is 90.9%, yet for him he set it at least 96%. And of course that wasn't really fair. But of course still it still works. After all, we are in Uganda. Anyway, that gets part A of the item 6, Aitel physics, UCE physics. Okay, part A of it covered. Let's go to part B. What do they want? So part B they're saying, sensitize the community on how the device would guard the transformer against such destruction. Now the device here we are talking about here is a lightning conductor. Take note of the SP. It is lightning conductor. Now you must know how lightning conductor works, by the way. But before you know how lightning conductor works, how do you think lightning comes about? I think we begin with that, then we come and get the whole story covered. Let's go there. Now still, we shall go pictorial a little bit, say that we can get this answered. We shall go pictorial a little bit. Now it all starts from there. Let's begin by getting a definition. What do you think lightning is? So we are saying lightning is a giant spark of electricity in space caused by. Now, what you should know is that lightning is simply electricity. Please see, I'm explaining how lightning comes about. How lightning comes about before we can go to how lightning can be stopped. So just know that lightning is simply electricity. And if it is electricity, then of course think about what you call what? If it is electricity, then think about what you call what? Current. Do you really see that? Okay, so we say lightning is a giant spark of electricity in space caused by an electrical discharge between two objects with very high or very large potential difference. Now, what does it mean? First of all, you need to know how lightning comes about. Now, what you should know is that lightning can only exist if a negatively charged cloud, like you see the negatives right here. The negatives right here. Now, if you study about if you study about nature, if you study about nature, you realize that on Earth, most of the objects are always positively charged. Now, what happens is, on Earth, maybe we can just say, okay, allow me to erase off this. Now, what happens here is that these are the clouds. Those are the clouds. Now, we have the trees right here. Now, the clouds will come with very many negatives. And once the clouds come near, of course, when it is raining, of course, don't expect a cloud to come near the surface. Of course, someone will look at this distance and just be like, I think I can't even touch this cloud. Not really, my dear. I'm just meaning like, in terms of rain. Now, what happens here is that when the clouds come near, or in terms of rain, the raindrops come along with these negative charges. As these negative charges come and arrive at this point, what does it mean? Remember, whenever you have a negative and a positive, like this, the electron flow is like this. That's how electrons flow. But again, like this, if the flow into that kind there is the current flow. It means that whenever you have a positive and a negative, expect current to flow. And we really see that from a negative to a positive, current is really flowing. Now, that current there is what we call lightning. But of course, it only becomes lightning if at all it is bringing more problems or more harm than good. How? In fact, this current can easily flow into the earth. Remember, the earth is an equipotential surface, meaning the earth can even absorb 1 billion volts without any harm. So that current can easily enter the earth. But where the problem comes is, if you have a tree or a building around here, as this current is trying to flow, the tree has what you call what? The tree has what you call resistance. In simple terms, the tree has what you call resistance. Now, this resistance to current, resistance to the current generated, resistance to current is what we call lightning. That resistance can lead into production of intense heat, too much heat, which can even burn down a building. And that's how lightning comes about. However, lightning is in types. For the one we're going to deal with today, or the one we handle as far as O-level is concerned, is what we call cloud to ground lightning. Please, we have cloud to cloud lightning, but here we're going to deal with the cloud to ground lightning, whereby the spark off happens just on the ground. Okay. Now, of course, I know you keep asking yourselves that why is it that lightning only strikes the tallest buildings? Why is it that lightning only strikes the tallest buildings? Okay, as lightning is coming along, or that current is coming along, it comes and gets attracted to any positive charge. So you find that as the time is coming, there is a positive charge at the highest point. Of course, there are very many positive charges. There are very many, but the one at the highest point, of course, that it will be the one on that tallest building, that tallest tree. Or if you're in the field, you'll be the tallest at that time and carrying maybe a positive charge on your head. And once this comes, the negative charges around, they will get attracted to this. Now that current will want to pass through your body, but your body has a certain resistance. Intense heat is produced and you can easily be burnt out. Anyway, God forbid. We pray that doesn't really happen to any of us. Alright, however, it is an unavoidable circumstance. You realize that in the United States, almost 49 people die of lightning strikes every year. 49 die of lightning. In fact, it's some big number anyway. In Africa here, we rarely receive such kind of. Okay, now we have known how lightning comes about. Now just imagine if that lightning has come like that, like in this question, and we have maybe our transformer on this tree, on this electric pole, sorry. our transformer will get damaged. But now we must get a mechanism, a device, which can stop that current from flowing. How do we do that? Anyway, let's get into that again. Still, let's go here. Okay, now it all starts with this guy here. It all starts with this guy here. And the note must you know is that now this one here, this one's here, these sharp points here, we call them spikes. Those sharp points there, we call them spikes. This is a spike. This is a spike. Alright, good. So this is a spike, these are spikes. Now there is something I want us to know. There's something I want us to know. It all starts with this guy here. In fact, you have all ever seen that even in some tall buildings or even some schools, and I think all the use schools, the government schools, be it primary or secondary, and some private schools, they have what we call a retaining conductor, by the way. Others, I think God's mercy is the one which saves them in the long run. Anyway, let's see how that guy works. Now it all still begins with this one here. What you must know about lightning, which words must you not leave out as far as lightning is concerned. Now let's understand this word, what we call corona discharge. This word here, corona discharge, that's what I want us to look at. Corona discharge moves with this statement here at sharp points. Now there's what we call action. There's what we call action at sharp points. You must be in a position to know. In fact, you must know this first of all. Action at sharp points. Now what must we know about sharp points? What must we know about sharp points? Now it is known that, I'll take you back to this picture again. Now action at sharp points, allow me to explain using this picture. Now they say that if you have, assuming you have this, you have that shape, then also you have this, a pear-shaped conductor. Okay, we have that. You all know about this in electrostatics, I guess. Now, what we call action at sharp points tells us about, action at sharp points tells us about, tells us about distribution. Tells us about distribution of charge. That how are the positive, how are the charges distributed on a conductor. Now, here, when you have these charges will be distributed in this format. If you can really look at it, look at that. Okay, here, if you can really be keen, if you're keen about this, this is how charges will be distributed. Charges will be distributed like that. I want you to notice something right here. There's something I want you to notice here. Now, okay, then here charges will be distributed like that. Now what you must know is that action at sharp points tells us that at the corner points, these corners here, the sharp points have many charges. Like that. That implies that whenever you have, now you do ask why are these spikes made so sharp. Whenever, if it is so small, so sharp like that, it will have very many charges right there. Very many. So bear in mind that all sharp pointed objects have very many charges at them. Of course, you'd wonder why did they use something of this kind. It's because of what we call corona discharge. Corona discharge is comes with what we call the distribution of charge on a conductor. That, okay, in simple terms here, what you should take is that if you have a small, if you have a small area, then we have many charges. I hope this can really make some sense. Then you have a big area, then we have few charges, and that explains why the spikes are made of very small area. Hope that really makes some sense. Now, what does it mean? Action at sharp points means this. It means this, that since the charges here are very many, I have to explain the statement action at sharp points. But remember, as you are here like this, just know we have air around, and this air has both positive and negative charges, and positive. You have them right there, positive and negative charges. Now, what you call action at sharp points is, you all know that if you have a positive and a positive near to each other, these ones here will repel away. If you can really see that. If you have again a negative and a negative near to each other, they will again repel. Like charges repel. Meanwhile, if you have a positive near to a negative, these guys will just do what? Attract each other. They will just attract. In fact, here we have what we call attraction, and here they will do repel. Not must you know, if here they are repelling, what must you know is what we bring here. Now, since we have positives on these spikes already, allow me use this area. Since I have positives on these spikes already, it means that the positives, what will they do? They will attract the negatives near to them. Then they will push the fellow positives, will be repelled far away. Repelled far away. Like that. Now you're seeing that this positive here have been done what? Have been repelled. If you can really see that. Meanwhile, the negatives here, they are attracted. They are attracted near the positive charges. If you can really see that. Now, what is happening is what we call action at sharp points, or what I've explained there is what we call ionization. That now even the positives which have gone this side up in the air, they'll also find air up there, which air has both the positive and negatives. Again, it repeats. These positives will attract the negatives near to them and push other positives far away in the sky. That's what we mean by action at sharp points in simple terms. Now, back to this picture of ours again. Now, what must you know? I've explained. Okay, allow me to erase of this. Okay. Now, sharp points, small surface area. Now, the sharp points, like you're seeing this spike here, it is very small, very sharp, and has small surface area. However, it has many charges. It has many charges. If you can really see that, it has many charges. Now, high charge density due to small area. Now, if the charges are very many, we call that high charge density due to small area. Now, what do you expect? We have what we call ionization of the surrounding air molecules. I've explained ionization. Okay, I've already explained it. That point whereby the positives attract negatives and push away the fellow positives. But even the fellow positive which has been pushed away attracts another negative up in the air while pushing other positives. Again, this positive that pushed attracts negatives near to it and again pushes the positive. It is a continuous process as it continues up in the atmosphere or up in the air in simple terms. Okay, good. Now, the positive charges apparently, anyway, let's talk about this and that. That's how the whole story begins. Now, this guy comes into play. But of course, guess what? As you're seeing the spikes right here, there is some metal rod connected to it going down. What is that metal rod there? What is that metal rod there? That metal rod, in simple terms, that metal rod is copper. It is a copper plate. Why copper? Because copper is a good conductor of electricity. If you can really look into that keenly, or it could compare. No, in some others, in fact, in some countries like USA, they even use aluminium to make, anyway, but it's not all that good. I think, just like you see that, anyway, don't want to go deep into that, but you have really, I hope you have got my point. Now, with that, we are now going to start with the action at sharp points. But first of all, before action at sharp points comes in, we must see lightning already in place. Remember we explained it, lightning comes when we have a negative cloud near to the surface. Now, what happens is, in simple terms, what happens is, alright, so what happens here is that when a negative cloud comes near, look at this, now this one is a negative cloud coming. Now negative cloud, with it has the positive, meaning that current will flow from there, like this. There will be some current flow. Please, when you have a negative and a positive, current flows from negative to positive. That's how we, okay, look at that. Now, as you're seeing that, just current will be flowing from here to that. Current will be flowing from here to this. Current will be flowing from there to that. Each negative matches with a positive on the spikes. But remember, these spikes here have a high charge density, meaning that the spikes have many what? The spikes have what we call many charges. If you can really see that, the spikes have many charges. And what does it mean? They will do what we call action at sharp points. What do we really mean by this? Now, what you're seeing here is a copper plate, like this, a copper plate. Now what happens is when the negative cloud comes near to this, okay, remember originally on the spikes, remember originally on the spikes here, on the spikes, like we have it like this, we have both positive and negatives. We have both positive and negatives right on the specs, just waiting for any action. Now once a negative cloud comes like this, what will happen is this, remember the negatives will repel the fellow negatives away. And now when these negatives have been repelled away or chased away, they'll look for a way. The only way out will be flowing through the copper plate. And we can really see that these negatives here are repelled to pass through this via this copper plate. Okay, via this copper plate, and you can really see the negatives right here going down. Now when someone is going to ask a question, where do they go? Of course, now we simply remind you that where they go is that we are reminding you that everything is connected to the ground because the earth is large enough and is at zero potential. Now meaning that it can absorb any amount of charge without getting significantly affected. So the earth can absorb any amount of charge or voltage. Even a billion voltage can be attracted by the earth, and the earth will have no problem. That explains why you have all ever seen when wires are connected underground. Some people, they are locally called camufos. When they make those connections underground, even when trains, when you're stepping on the, even when you're stepping down on barefooted, you don't really feel that effect. It's because the earth is at a zero potential, therefore does not allow or is not affected by any amount of charge which comes into it. So now we have ended on a story whereby negative cloud has come, the negatives have been sent away through the copper plate downwards. Where do they go? They go towards, they go into the earth. Okay. After that, now what happens? It means that at the spikes we only have positive charges only remaining. But don't forget, we also have surrounding air. Which surrounding air is this? Which has both positive and negatives, both positives and negatives. Now, what happens is, just know that the negatives, the positives which are here are not enough to, in fact, for lightning to stop, we must kill all the negatives which are in this cloud, kill them away. Once we kill all of them, then we shall have stopped lightning. But again, they are still around. Then what does it mean here? It means that we must call for what we call reinforcement. Reinforcement comes in a way that now these positive charges here must call for more help from this surrounding air, of which surrounding air is both positively charged and negatively charged. Okay, now what happens? We come in this place here like this. Alright, now what happens is, of course, now this picture is just trying to explain that when negative clouds come, the positive charges remain on the spikes, or we use the word induced on the spikes, then the negative charges flow downwards. I've already explained that in this picture. They're a bit related. I've already explained that. Here also this picture is explaining the same thing. Negative charges coming down to the ground. Okay, good. Now, in the so doing, what must we see? Now, next is we are going to talk about the ionization, or the action at sharp points. The ionization. Let's go there, I think, in the next part. Now, the ionization we're going to talk about is the ionization is now remember here we still have our negatively charged cloud still in the place. Now how does the ionization take place? I would explain that earlier on. Ionization takes place in the way that if you have the surrounding air, allow me to explain using this. This surrounding air has both positives and negatives. Just know they are in a disorganized way, positive and negatives. Now remember the spikes have positives. What will happen? The spikes here will repel the fellow positives. Allow me use letter R for repelling. Then meanwhile this positive will attract the negatives. Allow me use letter A for attraction. Now if they're attracting, what happens is that process of repelling and attracting is what we call ionization. Now that ionization, now like you're trying to explain here that negative charges are attracted to the spikes while the positive charges to the cloud. So as they are pushing away the positives, remember we said that in order for lightning to stop, I'll take you back to this. In order for lightning to stop, I explained here please that in order for lightning to stop, we must kill out these negatives here. And how do the negatives be killed away? Any positive which enters the cloud kills that negative away. Another positive which enters the cloud kills that negative away. So we need to get more negative positives and we send them into the cloud. In the so doing, we shall have stopped, or we shall have removed all the charges from the cloud, and therefore it will be harmless, or it will not be harmful. Let's get there still. Now what does it mean? It means that we are on the step of ionization. So in the so doing, realize that I'll erase of this. So in this process, The negative charges from the air are attracted near. You see, these are negative charges. The one is you're seeing in blue are negative charges. Meanwhile, what you're seeing here is the positive charges. They attract the negative charges from the nearby air, and what happens? They will repel the fellow positives. Now these positives, you see the positive charge entering the cloud? Yes. Now these positives will go there. And maybe what happens is, the positives sent, if say for example the cloud has 10 negative charges, then this, since it is a sharp point and has very many charges, with it can send over 100 positive charges. And guess what? The 100 will go and kill the 10, and even some remainder remains. Now once the negatives go, this positive can die with that, this positive can die with that, this other positive can die out with that, another positive dies out with that, another positive dies out with that. And guess what remains? Guess what remains? Now that happens because of the high charge density and electric field intensity, which cause ionization of the surrounding air. You may not use this kind of language, but I would explain what you mean by ionization. Now, what happens is, once that has happened, as the positives are killing each other, the positives which were sent up in the air are killing the negatives in the cloud. What happens? This is what we call, it creates what we call a space charge. A space charge, that the positive which has been sent up in the air, once it points another positive, it pushes it up until when they reach the cloud. That's what we mean by space charge. The word space charge can also mean what we call ionization. That process of ionization, that process of pushing positive, repelling positive, negative attracted to the positives, we call it a space charge, or ionization in simple terms. Now guess what? Once all the positives have been killed away, we now have our clear cloud. And with this, please, of course, you just know God has finally answered your prayers. By the way, God has answered your prayers. You should be happy. And of course, here the cloud is discharged. Discharged means that we don't have any negative on it. And the cloud without those negatives, it is therefore harmless. And therefore, your building will be safeguarded from that kind of damage. I hope that really has made some sense. Let's now get back to the written work and maybe we'll get that explained slowly. So let's get there. The saying. Okay, the saying, when negatively charged, of course I've explained all this, but we shall just go through it slowly. Let's get there. Let's get this explained. Let's get this explained. All right. Now maybe we'll go through slowly as we go. So the thing, when a negatively charged cloud passes over the spikes of the build of a lightning conductor. Now negatively charged cloud, I've explained how it comes about. Okay, how lightning comes about, we explained that. But of course, the negatively charged cloud may not, you don't expect clouds to come on top of your building, but what you are seeing as cloud may not necessarily be cloud, but it can just be a raindrop. Okay, so when a negatively charged cloud passes over the spikes of a lightning conductor, positive charge is induced on the spikes and the negative charges on the earth plate. Yeah, we explained that. We had the spikes right here, but the spikes have both positive and negatives. So when a negatively charged cloud comes around here, the fellow negatives are chased away, repelled from the law of electrostatics, and will flow down to the earth, because the earth is at zero potential, it can hold them. And what remains on the spikes? What remains on the spikes is only the positive charges. Okay, let's get into this. And negative charges on the earth plate, yeah, or the copper plate. Okay, since the spikes have sharp points, yeah, now of course sharp points have very many charges. Spikes experience a high charge density, a high charge concentration, meaning very many charges. There are very many charges at the sharp point, which create a strong electric field. Now a strong electric field meaning that there are very many concentration of very many charges in that place, meaning that these charges can affect the surrounding air. Okay, electric field. Alright, as a result, the air molecules around the spikes are ionized into positive and negative ions. I've explained that. That point of the positive repelling out the positives up in the air, and the positives also attracting the negatives near to them. That's what we call ionization. Therefore, what happens? The positive ions are repelled towards the negatively charged cloud. Now the aim, you know, here, when the positive charges are going toward the negatively charged cloud, is to cancel each other. So clouds where they neutralize. Neutralize means that once you have a negative here and the positive when it comes near to it, they will all die away. That's what we call neutralize some charges on the cloud. So the negative ions are attracted to the spikes. Of course, we explained that. Where they are neutralized, Now, just like we are attracting some of the negatives to the spikes, these negatives will go ahead to even kill some of the positives on the spikes. But of course, remember the spikes are very sharp and have very many charges. In a way that one positive charge is killed and 10 more are produced. So that is it. And some charges on spikes. So a discharge from the cloud is safely conducted to the earth through the thick copper strip. So we're like saying some of the negatives which are attracted near the spikes after ionization, they may be in excess. If there are too many compared to the positives which are here, those negatives there will be attracted into the spikes and via the copper plate up to the down to the earth. Okay, this leaves the cloud. Okay, allow me to resolve this. Okay, this leaves the cloud with no charge and it becomes harmless. Okay, and with that you don't experience any danger. That brings us to the end of this whole item 6 physics. Item 7 is also soon coming, and we shall get this paper done. Then we shall be dealing with anything else which comes by. And of course, please, you may also write to me in the comment, or you can hit on my inbox about what do you think we can upload next. Okay, thank you. I wish you well.